Okay, we're back in chapter 7 on part 5. And this slide talks about roller coasters and how we can use the conservation of mechanical energy to help us determine the speed of the roller coaster without basically knowing the details of the net force acting on it. So, if we wanted to look at the speed of a roller coaster through all its loop-de-loops and the hills and valleys, it would be kind of hard using Newton's second law because your forces are continually changing in magnitude and direction. But we can use the conservation of mechanical energy to help us determine the speed of that object without knowing the details of the net force. Now, we do have to ignore our frictional forces. So, by using this conservation of mechanical energy, we're able to calculate the mechanical energy if we know the mass, the speed, and the height of the roller coaster at a certain spot. We know that as the roller coaster loses potential energy, it's going to speed up and it's going to gain kinetic energy. So once again, we have one form of energy transforming into another form, which is all our conservation is about. So this slide shows some different types of energy forms. We've already talked about kinetic. We've talked about our gravitational potential energy. This picture over here shows us our elastic or our spring potential. And that is your potential that's stored as a result of deformation of an elastic object, like stretching a spring. Okay, it's going to be equal to the work done to stretch that spring. It will depend upon your spring constant, which is K. Down here, we're looking at thermal energy, and thermal energy is that internal energy of an object due to the kinetic energy of its atoms and or molecules. So it's that heat energy. Here shows us our chemical energy, and chemical energy is really just your potential energy associated with your electromagnetic force. Most of the energy that we use every day deals with releasing the chemical potential energy of our fossil fuels. And then this last picture is our nuclear energy, and that's going to be the energy associated with nuclear fission or fusion, especially when it's used to generate electricity. Your nuclear power plants are designed to release nuclear potential energy, and your nuclear potential energy is the ultimate source of energy that we receive from the sun. So this slide just talks about what I've just gone over. This picture actually illustrates the elastic potential energy, showing how the spring is compressed and then it can be stretched out. Again, going over what I just said, thermal energy, likewise chemical energy, and nuclear energy. So conservation kind of raises a question, is it something real? Because what we seem to be doing is that whenever we see a situation where energy doesn't appear to be conserved, we just invent a new type of energy. So how can it be valid if we keep doing that? Well, conservation of energy is one of our most powerful principles in physics, and it's one of the most powerful because it's general. The only restriction is that your system be isolated or closed. So your results are kind of reassuring, because if the results were different, they wouldn't have a valid scientific principle. So conservation of energy is actually a useful concept because of the mathematical expressions for dealing with the different types of energy. And like I said in the previous slide, it's one of the most powerful principles, and basically because its only restriction is that your system be isolated or closed. So this diagram right here shows you the different types of energy that are possible in the ovals. And if you notice, the lines and the arrowheads show the direction of transformation and what process is included in that transformation or named. So for instance, if we look at radiant energy, we can see through photosynthesis, it becomes chemical energy. Likewise, if I start with chemical energy, through oxidation, I get radiant energy. So you can see if I start with 2 joules of radiant energy, I have to wind up with 2 joules of chemical energy. Another thing we want to look at is power. And power can be calculated in one of 3 ways, depending on what you're given in your problem. So when you're doing problems with power, you want to make sure you make that list, seeing what variables you're given and what you need to know what of these 3 formulas you need to use. So let's go over them. So the first one is power is a change of energy with time. So you can see power, we represent it with the capital P. So power is delta E over delta T. Now, power also measures the rate at which energy is transformed into or out of a system as work. So power would equal work over delta T. Now, the rate at which energy is transferred to an object as work is also power. Power is the force, the product of the force that does the work and the velocity of the object. So power can also be calculated as F times V. New units for power is our watt. A watt is a joule per second. In the English system, we would use a horsepower. A horsepower equals 746 watts. Okay, let's try one problem before we break on this slide, on this part. So in this one, we're asked to calculate the work done in joules and the power in watts when an object weighing 100 kilograms is lifted 3 meters in 10 seconds at a constant speed. So we want to know what the work is, okay, and we want to know what the power is. We know our object weighs 100 kilograms. So actually, even though it's telling us it weighs, we know it's a mass because of the units of kilograms. It's lifted 3 meters, so we know our height is 3 meters, and we know our time is in 10 seconds. Okay, so we're lifting, so we know to find work, we have to do work is mgh. So we have 100 kilograms times 9.8 meters per second squared times our 3 meters of height. So our work is actually 2,940 Newton meters. Now, one of our formulas for power, where power equals work over time. So our work is 2940 Newton meters, and our time is 10 seconds. So our power would be 294 watts. Now you might be wondering why I put Newton meters. Well, a Newton times a meter equals a joule. Okay, this ends part 5 of chapter 7.